All right, so today we're going to do something a little different. Think of it like a live debugging session for one of the most common and frankly most frustrating glitches you see on the web. You update something, you hit refresh, and poof, it's like it never happened. We're going to dig into the architecture of what's called leader-based replication to see exactly why that happens and, more importantly, how engineers fix it. Okay, so picture this. You just found the perfect new profile picture. You upload it, you hit refresh, ready to admire your handiwork, and nope. Your old photo is just staring back at you. For a second, you're just confused, thinking, did I even click the button? What in the world is going on in the background to cause that kind of glitch? To figure this out, we've got to back up a bit and look at how this stuff is supposed to work. See, in any big app you use, your data isn't just sitting on one lonely computer. No way. It's copied or replicated across a whole bunch of servers. This is all for speed and to make sure that if one machine goes down, the whole system doesn't go with it. And a really common way to set this all up is something called leader-based replication. The idea is actually pretty straightforward. You've got one server that gets crowned the leader. It's the single source of truth, and it's the only one that can handle any changes to the data, what we call writes. All the other servers are followers. Their job is simple. Just keep an up-to-date copy of whatever the leader has and handle all the requests to just view the data or the reads.
Okay, so let's actually trace the journey of your data on this diagram. When a user on the left uploads that new profile picture, that write request goes straight to the one and only leader. The leader takes care of it, and then, you see those arrows? It sends that data change out to all the follower servers on the right. Now, when a different user wants to see that profile, their read request can go to any of those followers, which spreads out the work really nicely.
So, in theory, this is a pretty brilliant setup, right? You've got writes going to one place and reads spread out across a bunch of others. It lets the whole system handle tons of traffic and stay super fast. But, as we already know from our little profile picture problem, something in this perfect picture can go seriously wrong. Okay, so let's get our magnifying glass out and find the exact flaw here. Because the very thing that makes this whole system so efficient is, ironically, the same thing that causes that profile picture glitch.
This right here, this is the scene of the crime. Let's walk through it. The user sends their new photo to the leader saves it and sends back a little OK message to the user's browser. Instantly, the browser says, "Great, now show me the new photo," and sends a read request. But look where that request goes. It gets sent to a follower. And because of just a tiny bit of network delay, that follower hasn't gotten the update from the leader yet. And bam, it serves up the old, stale data. From your perspective, it's like your upload just vanished into thin air. So what's the name for this villain? The technical term is replication lag. It's that tiny, built-in delay between when the leader gets the data and when the followers get the memo. It could be milliseconds, it could be seconds. But that lag, that's the ghost in our machine.
All right, diagnosis complete. We know the bug. Now how do we fix it? The goal here is to achieve something called read-after-write consistency. It's a fancy term, but it's basically a promise we want to make to the user. And here's that promise, plain and simple. If you're the one who just made a change, you should always see that change when you reload the page. Period. We need to make sure you get that immediate confirmation that what you did actually worked. So how do we actually pull this off? Well, we introduce a really simple but super powerful routing rule. Let's go back to our mental diagram. Now, when a read request comes in, the system asks a quick question. Hey, is this person asking to see something they might have just edited, like their own profile? If the answer is yes, we do something special. We completely bypass the followers and send that read request straight to the leader, because we know for a fact the leader has the latest info. If the answer is no, like you're just looking at someone else's profile, then it's totally fine to send that request to any of the followers. And just like that, with one simple if-then rule, the profile picture problem is gone, solved. You've guaranteed that users see their own changes right away while still getting all the benefits of spreading out the other 99% of read traffic across the followers. But you know how it is in engineering. You fix one problem and it usually shines a light on a new set of choices you have to make. We fixed the lag problem for the user, but now we have to look at an even deeper question about how the leader talks to its followers. And this is a classic one, speed versus safety. And it all comes down to two main flavors of replication. First, you have asynchronous. Think of this like sending a text message. The leader just fires off the update to the followers and says, "Okay, my job is done," and moves on. It's super fast, but it's also a little risky. Then you have synchronous.
This is more like making a phone call. The leader sends the update and then just waits until the follower picks up and says, "Yep, got it, it's saved." It's way safer, but it can be painfully slow. And this diagram really nails the difference. See follower 1? The leader sends the data, and then it's stuck, just waiting for that OK to come back. That is our synchronous phone call. Now look at follower 2. The leader sends the data and immediately moves on to the next thing. It doesn't wait for a reply. That's our asynchronous text message. So here's the core dilemma. With asynchronous, the fast one, if the leader server crashes a millisecond after it told you your data was saved, but before it sent that update to a follower, that data is just gone, forever. But on the flip side, with synchronous, if just one of those followers goes down or the network gets flaky, the leader is stuck on that phone call waiting for a confirmation that's never going to come. The entire system can just grind to a halt, unable to process any new writes. So when you weigh those two risks, a total system freeze versus a tiny chance of losing a single piece of data in a crash, well, the system freeze is usually considered way more dangerous. And that's why the vast majority of systems you use every single day are configured to be almost entirely asynchronous. They choose to stay up and running over being perfectly 100% consistent all the time. Okay, so this brings us to the final and honestly, the biggest puzzle in this whole setup. We've debugged replication lag, we've weighed the trade-offs between speed and safety, but there is one giant failure we haven't talked about yet. What happens when the leader, the single source of truth, just goes dark? The process of seeing that failure, picking a new leader from the group of followers and rewiring everything on the fly is called failover, and it is one of the hardest problems in distributed systems. How do you make sure the best follower becomes the new leader to lose as little data as possible? How do you avoid chaos during a switch? That is a topic for a much deeper debugging session.